In this video, we continue our exploration of Python data structures by considering sets. Sets are also very similar to lists, but instead of being ordered, a set is unordered. A set can store heterogeneous data just like a list, and a set is also mutable like a list. But what does it mean to be unordered? Let's create a set and see what happens when we print it out. Notice that we entered the data into the set in the order Dylan 26, 176.6, and true. But when we printed out the set, it printed out in a different order. This indicates to us that the set is not an ordered object. But in fact, this property of being unordered goes beyond the idea of simply printing out in a different order than we entered the data. This representation does not mean the set is simply ordered as Dylan 26 true 176.6. One way to demonstrate this is to attempt to access the set by position. If we try to get the first element by position in the set by indexing into it at 0, we encounter a type error, and we're told the set does not support indexing. We cannot access items in the set by position. They have no position. This is what it's meant to be unordered. It's important to recognize that this is simply a visual representation of the set. It is not the set itself. And in fact, anytime we print an object to screen, we're not necessarily seeing the object in its truest form, but are rather seeing some visual representation of an object that may be more complex or too abstract to represent in a simple text form. So this unordered property principally means that there is no meaning for position in the data structure, indicated by the fact that we cannot access data elements by position. However, we can still access the data in the set. For example, we can pop items from the set. Here, when we pop the set, something comes out of it. Dylan. It's not necessarily Dylan because Dylan was first in the representation, since there is no order implied by this visual representation. It just so happens that Dylan came out of the set when we popped it. We can also add items to the set using its add method. Here, we'll add true as a string, not as a Boolean value. Similar to add is analogous to append for lists. It adds a single element to the set. Update is analogous to extend. It will iterate over a collection or container of elements and add them to the set one by one. So with the first line, we added the string true to the set. With the second line, we added the items 58.1 and brown. Again, we can see that they don't enter even the visual representation of the set in any particular order. It's useful to keep in mind that add functions like append for lists and update functions like extend. So why would we want an unordered data structure? It seems not to give us any advantage, but to severely limit how we can access the data in the container. The answer is somewhat subtle. Imagine that we have 10 boxes and 10 piles of money, and we put a pile of money in each box. There's a representation of this situation here, where we have 10 boxes and 10 quantities apportioned to each box. Now imagine that we want to find if there's a box that contains $5.37. How might we find this box? Well, if we were doing this outside of programming, just in a physical situation in the world, we might look in the first box, see that it doesn't contain $5.30, then look in the second box, then the third box, the fourth box, until we eventually come to the seventh box where we find what we're looking for. This might take a while, especially if we have a lot of boxes, and especially if the thing we're looking for isn't in any of them, in which case we have to start at the beginning and check all the boxes until we get to the end before we know that there is no box that contains what we're looking for. This is an illustration of what it's like to look for data in memory when your data is stored in a list. You start at the beginning of the list and look one by one through locations in memory in order until you find what you're looking for. When we're searching for an element in a set, it works in a different way. Imagine, for example, we still have 10 piles of money, but we have 31 boxes. And instead of putting each pile of money into the boxes in order, we instead calculate which box we'll place the money in based on how much money we're putting in the box. So to do that, first we'll multiply the amount of money by 100, and then take modulo division by 31. And whatever the result is, we'll put the money into that box. Here's an example of that implemented in code. Here are our piles of money, represented as a list of different values. We'll also define this function called hash function, which multiplies the quantity by 100 and takes a modulo 31. By applying the hash function to each pile of money, we get the location where we should put the money, which box we should put it in. Now imagine that we want to find if there's a box with $5.37 in it. We can figure out which box this pile of money should be in by simply applying the hash function to this quantity of money. Let's actually do that instead of writing out the mathematics. When we apply the hash function, we find that the money should be in box 10. So we can jump directly to box 10 and look in there. Box 10 contains the $5.37 that we were looking for, so we're done. Alternatively, it could be that there's nothing in that box, in which case we know this set does not contain a pile of money of $5.37. This technique of assigning boxes, or memory, locations, based on the object that the box will contain is called hashing. Hence why we call this a hash function. It makes searching for data very fast because we can directly calculate where in memory the data should be based on the value. Therefore, instead of having to search every location in memory until we find our item, we can simply calculate the hash function and go directly to the location in memory where it should be. However, this means that the positions in memory are meaningless. They don't have to even be continuous in memory. We can pull a bunch of memory addresses and use those as locations that our hash function can allocate data to. Therefore, instead of being a line of boxes, it's really kind of a random jumble of boxes in space. And our hash function tells us which box to open when we ask if an element is in the set. There's a there's a programming computer science book that I quite like called Problem Solving with Algorithms and Data Structures. So if you search for this book, you'll find it on the internet. It's a free book, and it contains a detailed discussion of many computer science concepts implemented in Python with examples. You can use this as an additional resource to our lessons in the course. And in particular, I think it has a very nice explanation of hashing in Chapter 5. If you're interested in learning more about hashing, you can visit this book. Since we have to hash the elements of a set, there are certain consequences for what kind of data we can store in a set. First of all objects in a set must be immutable. Python has a built-in hash function. We can use it to hash any kind of object so long as that object is immutable. If we try to hash something like a list, the hash function will throw an error and tell us unhashable type list. Why can't we hash lists? The reason is, if we were to hash a list, if we mutated the list later in our program, that hash for the list would no longer be valid. It would be outdated. And the list would not be stored in memory where it should be, because the value has mutated and the old hash function no longer matches the current hash function. Therefore, we can only hash immutable objects like tuples, strings, and numbers, or Boolean values. There's a number of other immutable data types that we can also hash, but those are the most common. Second, any objects in the set must be unique, since identical objects will end up with the same hash. Since we can't store multiple objects at the same location in memory, any duplicates will simply be discarded. Here's an example of where we've created two sets where the sets have some duplicates in them, like the number 23 or the letter C. We see in the resulting set that there's only a single letter C and a single number 23. I didn't mention this, but the syntax for creating sets is typically using curly brackets. However, we can easily convert other data types into sets by applying the set function, or the set type, around other containers, such as lists or tuples. Similarly, you've seen in a past example that I've applied a list to a range to convert a range object into a list. All the data structures we'll discuss in this series of lectures have this capability, as we'll explore later. Since elements, because searching for data in a set is very fast and simple, it's very easy to make comparisons between different sets. Drawing from set mathematics, or the mathematics of sets, we can easily calculate the intersection, union, or differences between sets. Here's a diagram of what these different things mean. If I have two sets, A and B, the intersection is the shared elements between them. The union is all the elements that are in either set A or set B. The difference between set A and B are all the elements in A that are not contained in B. And likewise, all the elements in B minus A would be all the elements in B not contained in A. We could also take a symmetric difference, which would be the union minus the intersection. All elements in A or B, but not in both. Here we demonstrate taking these different operations in code. There are intersection, union, difference, and symmetric difference methods of sets. So we have two sets, student A courses and student B courses. We can see both students are taking English and biology, but student A is taking history and theater, while student B is taking mathematics and computer science. The intersection of the two are the courses they share, biology and English. The union are all courses either of them are taking. The courses student A is taking that student B is not are theater and history. The classes student B is taking that student A is not are computer science and mathematics. The courses that either of them are taking, but not both of them are taking, are all the courses except for biology and English. Pause the video here and consider the following exercises. When should you use a set instead of a list? And what is an example of a problem where a set might be part of a solution? I'm going to create a question on the message board where you can add your answers after thinking about these questions. And we'll add some tags. Data structures, set, and hash, as well as exercise. In the next video, we'll discuss the dict data structure.